Welcome to Physics Made Easy channel, and now we shall be solving problems on dual nature of radiation and matters. And I will be starting with some shortcuts for solving numerical problems. Plus, and also the pitfalls. This part is important, but we will practice some typical MCQs from this part. Typical MCQs, they are very much important because concepts, once you solve those 10 to 15, about not even 10 to 15, 7 to 8 problems, MCQs, in fact, they are very much illustrative and the basics are through. And after that, it is your understanding and problem solving ability that will carry the day. So, first of all, we have got a concept of work function. We know that the work function is a form of energy that is required for a free electron to leave the metal surface. And before um, attending this session, I request all of you to go through the basics, either from your other sources. If you don't have other sources, then lecture about the basics are present on our channel. Kindly listen those lectures and do some writing work and then come to this problem solving. And here the first shortcut that I propose you. Sometimes you need to very quickly calculate the wavelengths. For example, the formula lies here. E in electron volt is equal to 1.23 into 10 raised to power 4 divided by lambda in angstroms. This is the basic formula that I shall be using. Work function phi naught is equal to h nu naught, and this is equal to hc by lambda naught. Kinetic energy of emitted photoelectrons k max is equal to half m v max square, and this is e v naught, and this is h nu minus phi naught. So we have got the basic Einstein equation. This is the basic Einstein equation. Maximum kinetic energy, one is given by the formula in mechanics, half mv max square. Another is formula we just write in terms of stopping potential. V naught here is stopping potential. ev naught is equal to h nu minus phi naught. V naught is the negative potential required to stop even the fastest moving electron from reaching the anode. Now, phi naught is work function. Phi naught can be expressed in terms of frequency. For example, this is h nu naught. This can be further expressed in terms of hc by lambda naught, and where c is equal to nu lambda. Phi naught is in joules, V naught is stopping potential in volt, H is Planck's constant, 6.63 into 10 raised to power minus 34 joule second. C and V max is in meter per second, M is in kilograms, and lambda is wavelength in meters. Now work function of sodium is given. Work function is given. Now he is asking us the question that whether it will show photoelectric emission with orange light. Now we will calculate wavelength corresponding to it. If the wavelength is more than this, then it will cause photoelectric emission. For example, for photoelectric effect to take place, lambda nu is more than nu naught, or in other terms, lambda nu naught is the threshold frequency here, or we can say threshold wavelength is larger than the wavelength. Now, if the threshold wavelength is larger than this, then photoelectric effect will occur. So, I will just the very basic principle of photoelectric effect is there exists a threshold frequency. If the photon incident on a metal has frequency more than the threshold frequency, then emission will take place, otherwise it won't take place. So in terms of frequency, nu should be larger than nu, not in terms of wavelength, lambda should be less than lambda naught. Lambda naught is the threshold frequency or the threshold wavelength. Threshold wavelength should be larger than this. For calculating threshold wavelength, I will take lambda in angstroms is equal to 1.23 into 10 raised to power 4 divided by, this is E in electron volt, and this value will turn out to be in angstroms. Now you just fill the values. This is 1, this is 12,300. This is divided by 2.3. If we divide it by 2.3, obviously its value is expected to be less than, you can say, 6,000 angstroms. So if this is less than 6,000 angstroms, so then emission will take place. One way is this. Another way to this lambda, one way of finding is this lambda is greater than lambda naught. Lambda naught, which is 12,300 divided by 2.3. It is roughly less than 6,000. Okay, na? To this equation, another way, you just find the energy corresponding to this photon. If you have to find the energy, then I will use the reverse formula. Reverse formula E is equal to 12,300 roughly divided by now 6,800. This is 6,800. 6,800, if we multiply it by 2, that becomes about 3, you can say about 13,600. 13,600. It means this is less than 2. And the photon of energy 2.3 electron volt is incident. It means the emission will take place. Why emission will take place? Because photon energy is larger than the work function. So in two ways, in this here we have found out the energy of the photon. In this example, we try to do the same problem by finding threshold wavelength. So the catch line here is this formula, this shortcut. Remember this shortcut, I will write it again so that very easy to remember. 1.23 into 10 raised to power 4 divided by lambda directly in angstroms. You don't need to convert it into meter or centimeter. Then you will directly get energy in electron volt. Or if you put lambda here, then E as this here. This is the one form of formula, and the second form of formula that I have just written here is this form of formula. Second is this form of formula. And in this form of formula, we are calculating lambda in angstroms when energy is given in electron volt. Here, when lambda is given in angstrom, we can find energy in electron volt. And now let us shift to the next problem. The work function of cesium is given. Find the threshold frequency for cesium. The wavelength of incident light, if the photocurrent is to be brought zero by a stopping potential, this he has given us stopping potential 0.6, you can say stopping potential is given. Stopping potential is 0.60 volt, and energy corresponding to this is 0.60 electron volt. So this is the, you can say this is K max or E max. We write kinetic energy by this. So this is K max is given to be 0.60 electron volt. Now, what he says, we will read again. If the work function is this, the threshold frequency of the cesium first. You can calculate lambda, and then there is also a direct shortcut for the calculation of its frequency that I will give you in my next lecture. The wavelength of the incident light. Now we have to give the wavelength of incident light. He has given us the work function. If work function is given, now E is the energy of incident photon. This is K max plus work function phi. Now this K max is given to be 0.60 electron volt plus 2.3 electron volt. So this is the total energy. So E is 2.90 electron volt. From here we can calculate lambda. If he has asked us lambda, very easy to calculate. Lambda is 1.23 into 10 raised to power 4 divided by 2.90 electron volt, and we will get this in terms of angstrom. So this lambda is 1.23 10 raised to power 4. This is divided by roughly 3. You can find out if we take it as roughly 3, then it will be 4100. It will come out to be around from here you can this is 4540 angstroms. He has given this in nanometers. So in this way you can directly use this formulas. This is not 3, this is exactly 2.9. So from here if you do the calculation, this is 12,300 divided by 2.9. From here you can find out the value of lambda. This is roughly 3. So its value is roughly, you can say, more than about 4,000 angstroms. So these are the rough guesses. So in this way you can find out this. And we have got another formula. Remember this formula. If we want to find out the frequency, I will give you the formula. Tomorrow. Next, the work function of a metal is given. This light of this wavelength is incident on it. What is the threshold frequency and threshold wavelength? This you want to tell what is the threshold frequency and threshold wavelength. Now the formula for the two set of formulas, this is the formula for calculating frequency if we are given energy in electron volts, and this formula is also very easy to memorize. This is 2.14 into 10 raised to power 14. 2.14 into 10 raised to power 14, 14 here and 14 here. You just substitute here E in electron volts. Now, what he has given us. Now, the work function of a metal is this light of 5000 is incident on it. Now, this light of 5000 angstrom, from this light of 5000 angstrom, you can calculate the energy of the incident photon. First of all, you can calculate the energy of incident photon by making use of this formula. You just fill here lambda in angstrom. Lambda in angstrom is 5000. And from here you can calculate the energy. And this comes out to be 12 300 divided by 5000. This is this, and from here you can get this is about 2.5. About 2.5 electron volt is the energy of incident photon. This is 2.5 electron volt, and the work function is 1.8. From here you can directly calculate maximum kinetic energy, which is 0.7 electron volt. Now if you have to find out the threshold wavelength, even that you can find out by making use of this formula. So basically here, these three formulas hold the key in whole of photoelectric effect. One is electron in electron volt, 1.23 10 raised to power 4 divided by lambda in angstroms. Lambda in angstroms, and this value is in electron volt. Or from this you can even calculate lambda is equal to 1.23 into 10 raised to power 4. This is in angstroms, and here E is the energy, and this is energy. You have to substitute energy in units of electron volt. Another formula, if you want to calculate frequency, then this is 2.14 into 10 raised to power 14. 2.41 into 10 raised to power 14. Make use of this formula. If you make use of this formula, you will get everything. Once you make use of this formula, then you will get everything. And now let us proceed ahead. So in this way, he has calculated here this new knot frequency. So here a bit of correction here. This is let me correct it. This is 4.1. Very useful formula for making quick calculations. Another is lambda in threshold. You can calculate all the frequencies. For example, threshold frequency. If you want to find out threshold frequency, you are given work function. Just fill the value of work function 1.8 into 2.41 into 10 raised to power. Let me correct it a bit. This is 2.41 into 10 raised to power 14 hertz. From here, it is approximately 2. If you have to just guess the answer is 4.8 into 10 raised to power 14. Roughly, this is the answer of threshold frequency. Similarly, you can calculate the threshold wavelength. For threshold wavelength, again, we can calculate this very easily. 1.23 into 10 raised to power 4 divided by E is 1.8 in electron volt. From here you can make calculations about threshold frequency. This can be calculated. Now, maximum kinetic energy of emitted electron is just, this is 0.7 electron volt, as I have already told you. This is 0.7 electron volt K max, because K max, it was just 2.5 electron volt was the energy, and if you subtract 1.8 electron volt, you will just get 0.7 electron volt from here. And from here, even you can get, if you have to just convert it into you can say joules, this will be 0.7 into 1.6 into 10 raised to power minus 19, and it will come out to be, if you multiply, this is 1.02 into 10 raised to power minus 19, from where even you can find out the velocity. So And the next is photoelectrons are emitted from a metal surface when ultraviolet light of this frequency. Remember, if frequency is given in nanometers, you just add one zero. Just add one zero to it, then it gives us frequency in angstroms. Is incident. Photons are emitted from a metal surface when ultraviolet light of wavelength. This is incident on it. The minimum negative potential to stop is this. They have given us the stopping potential, and it means the maximum kinetic energy is this. And now what he has asked, energy of the incident photon. This you can calculate very easily. From here you can make calculations of E. E is 1.23 into 10 raised to power 4 divided by 3000. It will come out to be 4.1. Roughly it will come out to be 4.1 electron volt. 4.1 electron volt is this, and this is the energy of the incident photon, and this is the maximum kinetic energy. From here we can find out the work function. From here we can find out the work function. Very easy calculations. 4.14, we have calculated 4.1 with shortcut. 4.14 is the kinetic energy. Kmax is just, you write E with volts, 0.54 electron volt. You just add them up, you will get the energy of the incident photon. And now he has asked us Kmax. The Kmax is difference of both of these, and that comes out to be 3.6 electron volt. With these volts, I finish this lecture, and in the next lecture we will start from here. And this problem is very important from your competition point of view, this problem. And there are two or three other problems which are very much important, particularly these two or three problems, this particular two or three problems, which we will take in my next lectures. So thank you very much for being with us for such a long time.